Okay, we're recording now. Duke, you have a question? Go ahead. No, it's just you notice a pattern. That's all. Like the pattern I know, like here I know it's 2 4 2 4 2 4. So again, it's position. That could be a pattern. So here the pattern is I see signs alternating, and I see that the denominators are all the odd integers in order. So it could vary. There's a lot of different ways this could happen. We are going to talk about very predictable patterns later in the week. Something called arithmetic sequences and geometric or arithmetic. Tomato, tomato, right? But arithmetic sequences are ones that have a common difference, like 2, 6, 10, 14, 18, and so forth. Geometric would be more multiplied by the same number, like 2, 6, 18, 54, 162, 486, and so forth, right? But explicit, let's come back to the notes here. Explicit kind of means if you have a formula, you can get it you get any term you want directly. So this right here is called an explicit formula. Because let's say for this pattern, I want like the 20th term. Now I got a formula I can plug into. So I don't have to start listing them in order. Sometimes that's not smart, right? Like if I said, oh, here's a pattern. What's the pattern here? What pattern do you notice for this one off to the left? Let me use different colors, guys. Sorry, guys. In pink. What pattern do you notice in pink? Or you multiply by 1/2 over and over again, right? So if I want like a 20th term, sure, I can multiply by 1/2 20 times, try 19 times after 1/2. But if I know a formula, that would be easier because I can get directly to it. Let's say I want the 108th term. Yeah, it's just easy to have a formula to plug into. So that's called explicit, when you can go direct. So for here, you're asked to write an expression for the apparent nth term for this. So basically, you're asked to write an explicit formula. So you have to kind of think somewhat out of the box. There are going to be some predictable formulas we'll use on Wednesday and Friday, but for now, we'll kind of just make up formulas that as we see fit. So, anyone want to take a stab as how I should make this formula for A? Brooke, go ahead. I like that. You guys agree? Yeah. I agree. Yep. Or you could write it like this. That works too. And actually, that's kind of important. What was that? Yeah. Assume n equals right. Great observation, Matthew. Yeah. Assume n starts at 1. Yeah. Assume it starts at 1. Yep. Yeah, that's good. Or you can write 1 over n plus 1. The reason that's kind of important is that we do see ultimately these terms will converge. Like if I go forever, like let's say I want like a millionth term, what do you think the millionth term would be close to? Well, by what, right? Because you think about it, this is a rational expression, right? If n's approaching infinity, the degrees are the same. So 1 over n plus 1, it's kind of nice writing. So this would just eventually converge towards 0, then to infinity. And the millionth term or billionth term would be 1. And that's what you guys are going to be doing in BC Calc. If you're talking about doing BC Calculus right now, they're doing a lot of sequences in series and looking at convergence. So we need to start thinking like that in some ways. But for now, we're just kind of understanding what a sequence says. What pattern you notice here for B? Yeah, just some, it's odd numbers, right? So how would you write it? How do you guys want to write it? Yeah, 2n minus 1 would be good. Yep, I'd agree. And then lastly for C, what pattern you notice here? Yeah, totally. N squared. Yep. Okay. All right, let's keep moving, guys. Yeah, what happened to you, V? All right. Okay, this one is not fun. To be honest, it's kind of a pain in the ass, but you kind of need to know because sometimes we don't have the luxury of writing things in a noticeable formula pattern, or if there's a pattern, but to write an explicit form may not be an option for us sometimes. Also, I mean, just to kind of say, if you guys are doing like the eight, like anyone gonna do the ACT in April or SAT, I don't know if they just, but I've seen this on the ACT. I've seen these kind of questions, and just mathematically, you just need to know what this means. So recursive, it kind of play on words here. Recurring. What does it mean something's recurring? Happens over and over again. Let's, for example, like once you guys get old enough, like have a credit card or investment account, sometimes you may want to have something recurring payments, meaning in the first of every month, just automatically pay my credit card using this checking account or whatever, right? Or automatically withdraw money from my checking account to my savings account or my retirement account or whatever, or called savings for my kids, stuff like that. So recurring means it just repeats over and over again. Here's how it works. Again, it's kind of a pain in the ass, but we'll do it. So we told k is greater than or equal to 2. So here's what we're going to do. We'll start with k equals 2. So a2 equals 2 times a sub 2 minus 1 plus 1, or equals 2 times a1 plus 1. Well, what's a1 here? So you get 7. Okay, and you needed this to get kickstarted. You need an initial value. You need something to get it kickstarted before you kind of like a car. You need like whatever. I don't know about cars, carburetors, whatever. But you need something to get the car started, right? So spark plugs. There you go. So it's kind of like the spark plug. Okay, next up, let's do k equals 3. So a3. I think you guys get the idea. Equals 2a2 plus 1. Notice how the output of the previous term now becomes the input for the new term. That's why it's recurrent. It's kind of like a function machine that way. Like this comes out and gets spit into the input to get the new term. So let's think about it. 2 times, what's a2 now? 7 plus 1. And you get, what was that? 8, well, sorry, I thought something a3 equals 2a2 plus 1, right? But a2 is 7, so a3 is going to be what? 15, you got it. Yep. Yeah, go ahead. Okay. Just because to tell you how to just to see how how to get started, that's all. Because you already know the first term, we need the second, third, and fourth, and fifth terms. Yeah. Okay, k equals 4. You okay, Yuvi? Nothing. We were worried about you. Okay. Glad you're back. All right, a4. So now you get the point, guys, right? Then a5. So 7, 15, 31, 63. So your first 5 terms, now I got it. It's going to be, let's say it's kind of a pain. 3, 7, 15, 31, 63. So you can see that, adding 4, I'm adding 8, I'm adding 16, I'm adding 32. So the common difference is actually doubling. How to write this in an explicit form, I'm not really sure. I mean, if I think one part, maybe I could think explicit. The recursive kind of is foolproof. Like you can always write recursive form for any. So, I mean, for any pattern. So sometimes it's just good to have in case if you can't think the explicit formula. Okay. Next one's called a Fibonacci sequence. It's a very famous sequence. All you're doing is this. So once you get the hang of it, what is this telling us to? It sounds like you're adding 2 previous terms to get the next term. So if you kind of know what's going on, you don't have to go about it in a painstaking way like I did in the previous problem. So what are the first 2 terms here? Yeah, and they decided to start at 0 for n, which is or k. So I mean, so be it. That's how they want to do it. Fine. But Now you're just adding two previous terms. So what's the next term going to be? 2. What's the next term after that? Next term after that. Next term after that. And there you go. That's called the Fibonacci sequence. So, and actually, there's some things in nature that kind of follow this pattern. I think like petals on a flower kind of follow this. I think. I don't know. I have to look it up. But so kind of neat stuff. Okay. So we're good at this? Makes sense? Okay. Okay. This is a fun one. I love factorials. This is like one of my favorite things to teach. And by the way, if any of you guys are interested in learning about like probabilities, like poker hands, casino games, stuff like that, more than happy to share some stuff. Just don't go gamble; it's not good for you. But anyway, but this factorials are used often in like understanding how poker hands, what the poker hands rank higher than others. So it's kind of a neat thing. Definitely one of my favorite things to teach. Okay, so a factorial is simply when you see this exclamation point and you count down to 1. And kind of a dumb joke, but like sometimes you say n really loud or say 4 really loud, like in golf, like 4. No, just kidding. Dumb joke. Okay. No, it's not an exclamation point. It's a mathematical term. Okay. Yeah, I stick with teaching math, not jokes. So yeah, you basically count down to 1. The only special case is 0. 0 factorial is 1. I don't know why. But all you do is just count down to 1 and you multiply it out. Like this is just 1. That's 2 times 1, which of course is 2. That's 3 times 2 times 1, which of course is 6. That's 4 times 3 times 2 times 1, which of course is 24. Write an expression for the nth term of the sequence here. So we notice the bottom is following the factorial pattern, right? So if I write an expression, I'd probably say a sub n equals, probably I would do, let me think here. I'd probably say n equals, start with n equals 0. And a sub 0, yeah, we'll just say that. Well, so yeah, you would have n over n factorial, exactly right. Exactly right. There we go.
Can you just do that?
I think I got it right. Did I get it right?
Just do that. Start at 0. Like,
Oh wait, I messed up, guys. Sorry, I messed up. I messed up. You want to do n minus 1 up top? Is that? You know what? I'm gonna follow you guys.
can you just say start at 0?
Oh wait, you can't do that on spot.
Hold on a sec. There we go, guys.
Yeah.
Well, let's be consistent. I've been starting n equals 1 for most of these problems. Let's see that. Sound like that. Yeah, let's see that. Which makes sense, right? Because the fifth term is 4 over 120. So there you go. Okay. Okay, guys, quiet, please. Thank you. All right, so let's actually do some simplifying. Here's the deal. A factorial can be written like this. Because what is 8 factorial? 8, 7, 6, 5, 4, 3, 2, 1. But if you think about 6, 5, 4, 3, 2, 1, it can be condensed to 6 factorial. And 2 factorial, of course, is 2 times 1. And 6 factorial, of course, is 6 factorial. So those cancel. Again, if you really want to be long-winded about it, you could have done all this. But it gets to be kind of time-consuming. But you can if you want. I mean, it's up to you, but I think this is a little cleaner. Oh, yeah, that's lame. For exponents, yeah. That's a middle school thing. So, but yeah, no, that's the trick, is that you can rewrite the factorial as one of the other factorials, kind of like a subfactorial, if that makes sense. Like in the case of B now. In the case of B, I can write as n times n minus 1 factorial. I don't know what n is, guys, but here's the deal. I know the next term is n minus 1, then minus 2, and so forth. So n factorial is higher. But by the way, the other thing I should tell you about too is that n must always be a whole number. It might have been mentioned on the previous page. I don't know. Yeah, n's always a whole number. Positive engine, not 30. If you put a whole number too, you put 0. But anyway, what cancels out here, guys? So you just get plain old n. Yeah.
I think we go on D. What's the difference
Mhm.
between with the parentheses and without them?
PEMDAS. 12 PEMDAS. Let's do C first, and then we'll do D. So for C, guys, which one's higher, 2n plus 2 or 2n plus 4? 2n plus 4, right? So the bottom is going to be, let me expand this just a tad, 2n plus 4. What comes next? 2n plus 3. And then now I see an opportunity to write just 2n plus 2 factorial. Boom, boom. What are you stuck with?
So just 1 over 2n plus 4.
Hmm? Yep. No, you want things to cancel. Now, to answer your question, Audie, about D. So this is like saying this. 2 times n factorial. And that's 2 times n factorial, right? So it's basically, it's kind of like a PEMDAS thing, right? So the factorial kind of takes precedence over multiplication. So this is going to be interesting. What we can do for here. No, because here's what's going to happen. You're going to have 2n times and down below, I'm going to have this. I'm not sure if this really simplifies as well as I want to, but what cancels? What can I cancel? The 2 and also an n as well. Yeah, I'm not sure if this really simplifies as well as I'd hoped, but
The 2n minus 1.
Oh, I think I know why.
Minus 1.
0 factorial is easy.
what?
Because like, you can keep going down with like n.
True, and then you have nothing left. Yeah. That makes sense. It's kind of like why when we raise them to 0 power, you get 1. Yeah, that makes sense.
2n minus like.
Right. Yeah, I'm not sure if this really was simplified. Well, no, because you have 2n. Wait, say again? 2 to the power of n. Hold on. Let me think about this one here. Let's check here, guys.
Yeah.
Wait, 2 to the power of n. Oh, I see what you guys are saying. Okay, let's back up a little bit here. Guys, let's back up. I think I know what you guys are saying. Okay, I think I got you guys. Okay, so you guys are telling me this. 2n factorial. So it's 2n. Actually, does that make sense? So wait, you're saying it's 2 to the n times n factorial? Is that what you guys are telling me? Doesn't make any sense. I don't think that makes any sense, guys.
It's just 2n factorial, right? Minus 1. Or 2, sorry, 2.
Yeah, I don't know. Yeah. Because you got to subtract.
The only thing that cancels the 2 and
Yeah, well, let's revisit that one later. Let's move on, guys. Okay, summation notation, guys. Let's move on. Okay, so this is also, guys, quiet. This is also very important notation, especially in calculus. You need to understand how this works. It's really simple. You just sum a bunch of terms. That's all you're doing, and it's usually for a finite sequence, unless if you see infinity up here, then that would be infinite. But usually it's for a finite sequence, and you're basically just adding up a bunch of terms. So this is how you get started, and that's how you end. That's how you get started. That's how you end. So, and you do it in order. So you do I equals 1, 2, 3, dot, 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 until you get to n, until you get to the last term. So what you do is you do this. And once you kind of recognize the pattern, then you could just, there's actually formulas you can use to make this a little easier. But for now, I'm just going to kind of do it by brute force. So 1 plus 1 squared, that's my first term, plus 2 plus 1 squared, that's my next term, plus 3 plus 1 squared, that's my next term, plus 4 plus 1 squared is my next term. So 3 times 4 is 12. Hold on. That's 27. That's 48. If I'm not mistaken. 75. 39, 87, plus 2, 162, I think. Am I correct in saying that? Okay. Now, guys, there's a way you can do this in the calculator. Here's how you can do it in the calculator. This is actually huge. So you guys see this. All right, here we go. If you hit alpha window, do you guys see the summation notation? It's option 2. And you can use x. You don't have to use I. So x equals 1, 4, 3 parentheses x plus 1. And there you go. Wait, what? Oh, squared. That's all right. That's my fault. Okay. There you go. Feel better now. Yeah, so you 162. So that's a nice little function in the calculator to help you out with that. Okay. So let's keep moving, guys. The next step. What you have to do is you have to plug in 3 first. And you add it to all the other terms. Then you plug in 4. You plug in 5. And you plug in 6. So you have -6 plus 8 plus -10 plus 12. So I think I get 4. Yeah, you get 4. Yeah. So yeah, that's that one. Questions on that one there? No? Okay, let's keep moving. And where I'm at now. Good, almost done. Here we go. So here now you're asked to use summation notation to work this out. So how would I write this summation notation? Oh, here we go. I'll use I. You can use any letter, totally arbitrary. Let's say this is I. And let's say this is I plus 3 times I plus 4. Does that make sense? I go from I equals 1. Ah, that should be a factorial. There we go. Yeah, the bottom should be a factorial. 1, 2, 6. Yeah, that makes sense. Does the top make sense? Yeah. 5. Yeah, the top makes sense. Now, you could work this out by hand, but now you know about the calculator. Let's use a calculator, right? So you get alpha window, option 2, x, 1, 5. And I'm going to do parentheses. Actually, you could probably make a fraction. Alpha y window, no, alpha y equals. You could punch in a fraction like that. X plus 3, x plus 4, and then x. To pull a factorial, you have to go to math, probability, option 4. Guys, quiet, please. So there you go. Guys, whatever you guys just put away, please. Thanks. All right. So 674/15. Yeah, that's all. Now for the next one, how many 3's do I have? 8, right? So you can see I equals 1, 8, and just 3 straight up. I know the answer is 24. I know that. But if you just put a 3 straight up,
All this means I want the 3 straight up 8 times. So I equals 1, my term is 3. I equals 2, my term is 3. I equals 3, my term is 3. I equals 4, my term is 3. I tell you I equals 8.
every single term is 8. 8 times. Sorry, it's 3. 8 times. So that's it. Exactly. Right. So another thing to keep in mind, if you do see a constant, you can pull the constant out. That totally works. As you see for number 2. And also, if you have a constant as part of the summation, it's just c times n, as we just saw for part B. And also, you can, if you're adding and subtracting 2 different functions or terms, you can break it up as an addition or subtraction of the summation notations. That works too. So these can be broken up, just so you know. Not times or divided, though. You can't do that. Not times or divided, but you definitely plus or minus you can. Go ahead, Evie. What's up? Okay. Okay, the last thing I want to talk about, sequences versus series. So a sequence, just so you know, is a list of numbers. With some pattern. A series is actually let me change colors. A series is an actual sum. You're summing up a bunch of terms in a sequence. And series is kind of what we're working our way towards, because that's what you do in calculus often. You work with things called series. And we'll talk about arithmetic and geometric series later in the week. The arithmetic series on Wednesday, geometric on Friday. So consider the following sequence, and it's infinite, means goes on forever. So the first n terms could be written like this, and that would be as a finite series or an nth partial sum. But infinite will, of course, be written like this, with an infinity symbol up top. And there's actually a course dedicated. Sometimes some people take a college course called Infinite Series, and it's a big part of AP Calculus BC. If you know what I'm doing AP Calculus BC, that's what we're doing, right? Or I think I did before break. It's a big part of the BC curriculum, where you work with this kind of stuff. So let's look at these 2 examples here, and then we'll call it a day. So you have to find the third partial sum, would mean that k equals 3. So you do 3 over 10 to the 1 power plus 3 over 10 squared plus 3 over 10 cubed. So you get 3/10. And just add them up, which I think is 0.333. So what do you think this is going to be generally overall? what do you think is happening?
Just add a 3.
Yeah, pretty much. I mean, for example, if k equals 1, I know I get 3/10, right? When k equals 2, when k equals 3. So what's the pattern here? What am I multiplying by over and over again? I'm multiplying by 1/10 every time, right? So the first term is 3/10. And the common ratio, what's the common ratio here, guys? What's the number I'll multiply over and over again? 1/10, right? So if you think about it, if I'm adding all these up, I believe we're gonna get 1/3 as the sum of the infinite series. I mean, it's kind of obvious that's what's happening, but there's actual a formula that goes with this. The formula looks like this. This is the formula for sum. We'll talk about this on Friday, so I'm kind of getting you guys a little ahead. Sum of an infinite geo series is the first term divided by 1 minus r, assuming r is between -1 and 1, non-inclusive. My first term is 3/10. My common ratio is 1/10. What's 1 minus 1/10, guys? 9/10. Thank you, Adi. If I simplify that, I get 3/9 or 1/3. So this actually does converge. This converges to 1/3 because my common ratio is between -1 and 1. When this happens, sorry, this is really, I'm kind of all over the map here, so my apologies. Let me erase part A so you're not confused by it. I mean, we kind of see that anyway from part A that, yeah, it's going to just be 0.3 repeating, which we know is 1/3. But there's actually a formula that goes with this, and it's called the infinite geometric series. Geometric meaning you're multiplied by the same number or have a common ratio between consecutive terms. So any two terms that are consecutive, the ratio between the one that's one higher than the other is always going to be 1/3. Or sorry, 1/10. So, and there's a formula that goes with the A1, the first term 1 minus r, and that's what you get. So, all right, we'll stop there for today. We still got 20 minutes. So the homework is right here. I circled a bunch of problems. So all I ask you guys to do is do the circle problems. I'm probably gonna do it on a separate piece of paper. This is from the textbook. They're odd problems, so I should have the answers. I should be able to post the answers for you guys. And the homework? No, it should tell you where to stop. I think there are 30 problems total for the first homework assignment. So I don't know where it stops. But there's 4 pages, I think, 3 pages. So yeah, so we're all done for today.